Hello, everybody. This is Majid, computer science PhD, and we have a topic that is a bit uh, more on the strategic planning level. Trying to get this thing away from.
That in a different screen.
Yeah, give me a second here.
Because
There it is.
right,
Oh,
that
we're
looks
good. Wait, where was I here? Okay, sorry for this glitch. So, although this is supposed not to be about AI specifically, but it's more about the next generation or the new generation of research in computational sciences / computer science. But I used AI as a use case to show, the the purpose of this research, the findings, and maybe some some recommendations. So that's one. Two, I used a case of Japan dilemma. It is a very well-known problem in Japan with AI, how they are not really be able to commercialize their AI efforts. Although for people who are in my age, they know that Japan is the old gangster of AI. Anybody who wrote codes in Prolog or studied AI in the 80s knows that. But as we're going to see from of these illustrations that Japan is really fallen, behind, we're probably going to, put out some analysis about the strategies of these countries in comparison. So we're going to address leading countries in the world, United States, China, United Kingdom, and Germany. So as you can see here, this is the leading actually illustration for the research today is the global AI index that utilizes 122 indicators grouped in 7 subpillars: talent, infrastructures, operating environments, research, developments, government, and so on. So these subpillars like organized under 3 main pillars: implementation, innovation, and investment. We think that these are the 3, not me, the people who build that, they know that these are the main key variables in this pursuant. So we're going to probably talk a little bit about AI policies, institutional models, and other technological capacities, commercialization of applications, and such to, you know, uh, shed the light on the key challenges and in the area of AI in these 3 pillars. So the figure is, this is like the index for 2024 heat map, top 10 countries. This is like a illustration for a comparative ranks across the key AI dimensions: talents, infrastructure, research, and so. And you can see that comparing like the AI readiness of key nations: Japan, USA, China, UK, Germany, using data collected, up to late 2024 around national strategies for AI in these countries. You can tell, obviously, USA is number 1, China number 2, and the rest we're going to probably talk a little bit about that. UK, Germany also ranking over there. And you can see probably weirdly that Japan is not on the list. Japan is currently in the 17th place ranking. Okay, so a little bit more, you can see the numbers here, like clearly USA scores like, on top 100 because the prioritization of fundamental research and innovation leadership. China with their because they invest massively and the goal is to be the globe leader in 2023. UK focuses, of course, Europe focuses on ethical AI and economic growth, and Germany a little bit of this plus leveraging industry, industry 4 with strong applied research. Of course, Japan, as it is known through their Society 5.0 version, aims to integrate AI into solving social-like challenges. Here are some of the readings about the I can't see from here. Anyways, so this is the USA in the lead. That's innovation driven by academic and industry. A very nice mix that we are trying to kind of follow, inspired by. There is a lot of talk at the end of this presentation about how I personally envision the future of the program that I'm leading, since I'm leading a research program, PhD research program in computational science / computer science. So we're going to talk a lot about technology transfer protocols and related things. So here are the some of the readings from the you can see like 109 billion AI private investments. Number one globally, 73% of the global AI compute controlled by the US, including in the other leading countries like in China. They are all rely on NVIDIA products. And there is like the strategy of decentralized innovation, the free market, entrepreneurship, startup ecosystems and elite universities, and then the opportunities with the NSF and other, funding sources. Here is what's in China. In China, there is a little bit different approach and strategy for AI. The least to say is that they are like building cities, supercomputers. They have huge AI companies, but the main maybe feature is the very strong support from the government to scale, speed up, and drive innovation. And technically, on the lower level of this spectrum, for the specialists in this domain, we know that although they use infrastructure that is American-made, the difference is the way they approach the algorithmic part of this pursuit as they go over to reasoning models that has logic and symbolic neurocomputing, and that's the cache plus some optimization techniques like quantization and other stuff on the low level programming of GPT in general that you currently probably living the era with. So now here is what's happening in UK. Strategic leadership in safe and scalable AI. So as you can see here, there are this strategy is featured by 10-year strategy pillars: invest in R&D, infrastructure skills, broad sectoral AI adoption, pro innovation, AI governance, and safety, and so on. So here is again in the United Kingdom some of the numbers that is invested in infrastructure boost, some unique regulatory approaches, and the startup and ethics strengths. And these words means a lot because they are very, very representative to the strategies of these countries. So whenever you see a slide that strategy does not have ethics, it means that country does not really pay attention to this thing. Okay, here's Germany. As we said, there's a dual focus on innovation, European values like privacy, fairness, transparency. There is public/private R&D. There is a model, Fraunhofer Institute, that bridges research and industry over there. And there are some other similar models that dominating like the domain. There's studies like top global research centers. TU Munich, that is one of the universities that I have great experience studying their model before I built the PhD, because it's a great mix of industry and academia, hands-on and theory, and commercialization of some of the solutions that a PhD students could come up with to help themselves in the analysis, stage of their research, but it still can be commercialized and monetized to any beneficiary. The challenge is slower AI commercialization and in comparison with the US and China. And there's still the regulations that is always a feature for any European strategy. The key vision is building AI leadership with public trust at the core. Here is Japan. Here is the dilemma of Japan. For the older guys who've been in the domain for a while, Japan was the top AI thing, even when AI was beaten up everywhere else. Anybody who studied the early models of AI and wrote codes in Prolog, that's what it is. There are some, Lisp was in the United States, but Prolog was the textbook all over the world for AI. But here is what is happening, because of strategy that they are like human-centered vision, the commercialization is a service of people, automated house services and such. There is kind of, a slow, or they're falling behind. They are in the 17th place now. So the key challenges in scaling AI innovation anywhere. 4 critical things: the generative AI infrastructure gaps, workforce development policy innovation, ethical and regulatory framework evaluation, and private public partnership. So the key points here are like, the infrastructure, compute, algorithm, and data. Who has it? As we said, the United States has 73% domination of the infrastructure. Even competitors like China are using, NVIDIA products. The way we invest in these, infrastructures, is it only for compute? So you go after the language models and consume, energy in a very intense way, or you go toward optimization algorithms and data, modeling. That is actually what is the current models in China claim that they have beating the American models. Again, some of the readings, some of the challenges, the lack of access for high performance computing. This is why above this room, exactly 2 floors, where 7 years ago, before we started any research program in PhD, we decided to build a high performance computing laboratory, because that's where you got to bring the horse first. And then, so other access is now becoming appealing, more than having your HPC and spend money for the one that you have on premise. Depends on how much you're engaged with industry. It depends how much you're engaged with research centers trying to do. Here is the other point: the workforce development and the AI talent pipelines. All what I can say, maybe out of what is here, is that this thing is very multi-headed when it comes to talents. Everybody now can be an AI creator. People who cannot write codes, there are tools we're building for them to drag and drop and build an agent and deploy it. People who can write C++ right away on the machine and be entrepreneurs and sell solutions, we're also supposed to accommodate. So we're talking about like, a range of ways to innovate in AI that need to be considered. AI ethics and policy divergence. No single strategy here. It's just like you can see, we address ethical stuff here, and we give entrepreneurs more, liberty in doing stuff. In Europe, more restricted. In China, even, I don't know, and stuff like that. So this is one of the things that needed. This is maybe the key slide. It is the public-private partnership. That's how I thought I should have built this PhD, based on RTL, based on transfer learning protocols with the industry, so we can again have the students do research as they are building maybe analysis tools in one of the stages of the research. This tool can be sold to somebody else, and we can get benefit, and everybody kind of pay their dues. These are the strategies in general. I want to excel a little bit so I can get into the main point of this. One of these strategies is that what should universities do and how they envision the future of AI. They're supposed to be aligning themselves with industries and maybe learn from other strategies and avoid mistakes. It depends on the goals that we're setting for ourselves. Here, what we have done, very simple. We're a very small university. I'm an unknown person, but I thought, why not? Since I have the opportunity, given the liberty to build things, so I thought, okay, let's run this thing and build a program that would be a tech venture launchpad, bridging research excellence and real-world AI innovation. Again, I have about 19 students. I think 7 of them are about in the business of building things, and they can monetize the tools, not the research yet. Because for the research, the computer science program PhD is no less than you have to come up with an innovative solution that can make you an entrepreneur, this is the least, or a patent product. So into this, a lot of details. This is like the map that the program is about. If you are, puzzled with the abbreviation, so K is always for knowledge, T is for transfer, P is for protocol, L is for level. So TRL is what we have been kind of trying to align ourselves with, skipping stuff and back and forth, just so we can sit next to somebody from Carnegie and they would, they would think that we are just like big research, establishment, but then, oh, okay, good to have you. But it has been gone very well to us. We paid some visits to some big universities and some DARPA contractors, and the ideas that our students are working on are really attracted everybody. Here is the core thing that we thought we can do. It's in neurocomputing, so we're computer science. We're supposed to be on the lowest level of creativity. So we write codes in C++, maybe a little bit of PyTorch, right away on the machine. And here are the things that we thought we can do, came naturally, not by analysis, but that's in every one of these, circles. I have 2 or 3 students that are doing one of them. Like to upper left, knowledge engineering and discovery, I have Don O'Hara, who is sitting here, building some of these models, and we were able to build some agents, and we deployed these agents to simulate the process of Delphi, which is bringing consensus about, in a team. And we gave the agents attitudes, and they clashed with opinions, and it was very successful and nice experience. Here are the resources of this. This is there is a lot to be said about this thing, and I'm open for questions. You want to use this computer or this?
Can you use yours? Is that okay?
Yeah.
Is this yours or in the room?
No, this is mine.
Oh, then I'll
Should I stop it?
Yeah, you can stop
Yeah.
here. Yeah, I'll get his.
Yeah.
Right.
Should I leave the session, or
No.
I will just stop the recording? You got to separate recordings.
Yeah.
Yes. Okay.
Okay, so
Oh, well, let's keep it going.
So-
Oh, go ahead, sir.
yeah, so yeah, good.
Sure, sure, yeah.
Implementation.
It's my footprint.
Yeah, so what is the main also this analysis? So maybe goal is to build a PhD program at HU or maybe
Well, this journey started long time ago. I was teaching AI in University Baghdad. I wrote my first neural network in 1995 to fix disturbed satellite images for the Air Force, the other Air Force. And it was a joke. Neural network was a joke. People use that with us like you're cheating. We could have cheated, but it was so. And I stayed following up. The day when ChatGPT came up, I was the happiest person, seeing the devastating on people's faces because nobody believed. But to your question, yes, the PhD program started about anything other than reverse engineering machine learning. The old simulation, scientific simulation, scientists used to do using computers and writing codes. But then now AI is the leading thing, not only because of the industry. When you want to produce a software right now, the first option, are you going to make agents and deploy them? So that's like became one of the things. And the university has an effort going for a while now, part of the strategic planning to figure out what we're going to do because it's coming at everybody. So that's what motivates the whole thing.
so if we develop the PhD program for AI support, then it will be inside the CIC or PhD program.
It is one of the, so you have the undergraduate, the master's, and the PhD.
PhD AI.
Yes, it is within. So I have other students who are doing stuff, but it is mostly, maybe not machine learning, but the guy doing robotics. Still.
It doesn't
Okay, so
look at you.
okay.
You can come up. No, he is the next presenter.
Yeah, and you mentioned ethical AI.
Yes.
What is the ethical AI?
Just
As-
one last question, okay?
As I said, there is no rule book for now because just like anything, you need a basic definition for things. How far you could go. There is a lot of, social issues in it. There is a lot of politics because now this thing is slaughtering everything else. The main people who are playing every role in our life are what? Google, Amazon, software, AI stuff. All the money, all the power, changing everything. So ethics is still now, you got to figure out. Especially.
Thank you, Majid. Yeah, we'll have our next presenter, Ham, right? Talk about AI tool, and then I will share the screen for you. You can come up. And share the screen. And, this will be your presentation. Okay. This is your slides. Yeah, go ahead.
So, hello everybody. So, I'm Sagar. You can call me Hema, whichever you want. So, let me introduce myself. So, my full name Enluri Hem Sagar. You can call me whichever you want, as I mentioned. So, I have 5 years of experience in data science and AI, and I completed my first master's back in India. So, I'm from India. So, here I'm pursuing the final semester at HU. So here, one of the AI tool that I have used, open source models from Meta and from Google. So by using those models, so I would like to show you one like a kind of POC to solve real world problems. So here, as you see my title here, multimodal RAG with the Streamlit. And yeah, so multimodal is nothing but it's going to act if you're going to I'll give you an example. So right now we are generating so many data, kind of videos, images, and text and everything. So here multimodal is nothing but it's going to calculate, it's going to manipulate the text data and images data and videos data as well. So here I'm giving the overview here. Once you have the files, like kind of PDF files, PDF files may consist of images and tables and text as well. Now, I would like to emphasize here, once you upload your file, you are able to chart over the PDF which you have uploaded by using multimodals. So the short form is RAG, is nothing but a retrieval augment generation. We are going to retrieve the data from the existed the output or existed the PDF. So going to the next slide. Here, I'm giving the some kind of high level introduction and the purpose. So you see, highlight the need of integrating retrieval mechanism with generative models to enhance response accuracy. So here again, as I mentioned, this is about introduction. So why we need a, multimodal? So as of now, in the market, there are so many models. We have text models, we have normal open source models, but why multimodal is, so you have the PDFs. Let's take an example. In the PDF may have, I mean, images, charts, and text, and tables, and many more. So multimodal can help us to solve all the problems. So it can able to read the images, it can able to read the videos, and it could also generate the text for you. So this is why the multimodal that I've chosen for the POC to solve the real world problem. So here, as you see multimodal here, the four pictures, the eye is nothing but the videos, and the ear, that is symbol that multimodal can able to learn, like decategorize the audios as well, and text and images. So going to the next slide, our project objective is here. You see the right hand side, some table and chart. So why I'm showing is here. So once you upload such kind of data, multimodal, it's a large language model. It can able to read the data, the tables and images as well. So you don't need to tell them. You don't need to tell the model. So this is the chart. This is the bar chart. Model itself able to learn. This is the bar chart. What all the data that we have inside the table, model can able to purchase. I mean, it able to capture it. So this is how the multimodal was useful. So going back to the normal rack. So I used multimodal rack, but in the previous time, people were using normal rack, but it cannot support images and tables, text state. Only supports text state only, excuse me. It cannot support images and tables, it cannot extract. So that's why I'm moving to the one step ahead with multi-modal rack. So here, as you see, the key features: upload the PDFs and context and images. It could also able to generate encoded all the data, including images and tables as well. And it also synthesizes the data for you in a well-structured format that going to store in database. So going to the next slide. Here, my entire architecture overflow. At the end, I will also show you my POC, like kind of uh, 20 seconds of video before going to the components like front end and back end, back end, and the vector, store, and LLMs. So here I'm using 5 components which are very crucial to build multimodal rack, because front end is important to upload, where you're going to upload this kind of file. As you see this slide on the right hand side, the PDF file you're going to upload. For that, we need a front end. The back end, we're going to use the orchestration, kind of lang chain, and we are building a huge kind of to handle the PDF files. So, and embedding is nothing but what are the that we capture from the data, that could be images and tables. We are turning them into a numerical form, because uh, human can read, understand the text and images, but machine cannot understand. So that's why we are turning them into a numerical form. That's called embedding. Going to the next fourth one, kind of vector store. So vectors is nothing but we are storing all of them in a vector way. So in a database, a kind of database it is, because in the previous time we were using SQL database and Postgre and MongoDB. So these are all our wallets. We can be used for text. Uh, Recently, I mean, not recently, going forward, the people, many companies going to integrate the new data with a vector store. So this is the easy way to get the data. So one of the example that I mentioned here, phase. The phase is nothing but a meta It's from Meta Vector Store. So there was it's open source. Anybody can use it. Um, Full form is phase is Facebook Facebook AI intelligence and similarity search. The vector stored database is work on similarity search. So similarity is nothing but when you ask the question you would like to query on the PDF, you'll get a response in a similar way, which you have uploaded and combined. And come to the last one, LLMs. So I used billions of Llama 3.2 billion parameter model and Gamma 3.4 billion for the images. So I used two different models to handle this data. So going to the next slide. So this is the data pre-processing the steps. So every data science they know what is the pre-processing steps which are very crucial to complete before we build the machine learning model. So here the first step is file upload and file parsing. File parsing nothing but a so inside the code, the backend it will work. It will extract the text first, and it will go to the tables next, and it will come to the images. So this is the step by step the process. Parsing is nothing but we are parsing the data and the data chunks. So we are not going to store entire the data in database, but instead of we are making chunks and we are storing them in database. And embedding generation, as we know, here I was using open source model for embedding because it's going to make the process easy to retrieve the data from database. And going to the next vector store integration, as I said, so phase I used from the Meta, and the retrieval mechanism is nothing but a you process user inputs a query, nothing but a question. So suppose the question is like uh, going back to the this slide. So I uploaded this file. I'm asking I'm asking the model, tell me what chart I uploaded and what are the values it has. So that kind of user prompts, user queries could be like that. So and then system retrieval relevant embeddings from retrieval, and retrieval data includes both text and images related information. Whatever that you ask the question, the model go on back and find the data, and then it's going to give you the best results. So that's called retrieval mechanism and answer generated with LLMs. So whatever the model, the retrieval function did, suppose you asked about, tell me what the diagram is, and model could able to give you the response. Once it received the response, it going to frame it as user understandings. So it's going to give you the well-structured format. So that's what we are using here, the machine large language models. And user interface, as you said, as I said, file upload session and query input field and display the area of area for generated answers. And I also added some screenshot. And so handling multiple users uploads. So here I would like to emphasize whatever what we have uploaded, uh, not only for one user, multiple user can be able to access it. So this is about it, and the challenges and solutions. So challenges are way there. So right now I'm facing some challenges. So I have developed this model. Now I would like to deploy it in cloud. So right now I don't have any investors. I'm just looking for any investor who could help me to provide this service to the many users, like many people, to solve the real world problems. As I'm since student, I'm looking for opportunities and the future ideas. So once you not only not going to stop here, I would like to make it as an app, and I would like to integrate in a different sources, so people can solve and easy to understand it. So that is what a summary. Before we go to the question and answer, so here are my reference and resources. You go my GitHub and you can find all the code and which I have created. You can download it and you can run it. So you can you be very familiar with this. Before we go into that, let me, so this is the demo which I would like to show you. So this is the front end which I have created, and the browse files here, you're going to upload the files. I have uploaded two files which has images and tables and text data. So once it's been uploaded, next, let me run this. It's been running. So it's been running. So So once it's been running, so you can ask questions like this. So I'm going to pass here. What the question that I asked here, what trends can be observed in the chart? I am asking about the chart, which I have uploaded through PDF file. So here it was showing the category D has highest value and the category A the lowest value. It's describing the entire the image. So this is how we are going to solve the real world problem. This is how we are going to solve and helpful to the every student, not only for the student, it will available, should be helpful for the every client. So even I will give you an example and let me continue it. So I'll give you an example. Suppose you have a kind of a 550, 100 kind of pages. You don't need to go and search and everything. And you can also, sometimes you don't have time to solve the problem. So the time these applications were useful to run it and to answer your question on the spot will well structure it, and along with it also going to bring some other content if you want to give you some other results. So as for now I worked on AWS and cloud and Google's cloud, so I used many resources to solve the real problem. So this is all about my presentation, and thanks for uh, giving me this opportunity. And as I said, I'm looking for opportunities whoever available and come to me. So I'm ready to go with the next steps. And thank you. Open to questions.
Okay. Okay, so if you go to the page 2, you mentioned so you will develop some kind of application to understand textual and visual data.
Yeah.
It's already all AI tools understand textual and video,
Mhm.
audio, all data. So
Yeah.
different from yours.
Yeah. So basically, what they're providing, it's all paid services. And it's also what they're giving is it's kind of limited sources. What we are emphasizing here, we are open to everyone. We are helping them students to learn.
That's okay. So all tools open to everyone. So we don't need to pay for them. They are free for them.
Yeah.
So yeah. So what is the difference
Yeah.
between first and theirs?
Yeah. So basically, everybody they're going to suppose you take AWS and which is different sources. You're going to upload it. You have to pay for such an amount. So when you come to the kind of open source models, so I used here OpenAI. So once you upload the file, here not only so as you said that's correct. There are many sources, but you have to pay. So when come to this point, so which I have created.
Like said,
Because that is pretty good.
Yeah. Yeah.
It's paid. So
Yeah.
but the yours will be free for
Yeah. So because once with the yeah,
still back.
yeah, for still back.
Help as a middleman
Yeah.
between the user and they crush you.
So my only intention is here whoever going would like to use and research help so I would like to help them to find the best resource to understand the basics. So obviously if you have large data, you should go for OpenAI. If you directly start with OpenAI, there will be a lot of amount you have to invest.
So this is very specific
Yeah.
to reading PDFs.
Yeah.
What kind of PDF?
It kind of this is especially I created to test the my own knowledge and along with machine learning, I mean large language model test. Because so if I take any other sources, if I give it,
That's a PDF.
yeah,
Scanned or it's a PDF. Regular
it's scanned.
graphical PDF.
It's scanned PDF.
Did you
Yeah,
consider
yeah,
limited scan
yeah.
or noisy
Mm,
images?
Yeah, I created with noisy. You see, as you see, it is not like a original PDF, and I just copy paste. I took screenshot and then I uploaded to the file, and then the model able to learn even when you scan it. If it's nothing but a, so you can read.
So here is a link for you.
Yeah.
Pauline Long is one of our PhD students who had a patent that the university couldn't benefit from it because we don't have a policy for reading corrupted PDFs and
Yeah.
bad, can, noisy.
Yeah.
There are as well 10 projects out there for BTP. So
While you guys keep asking, I'm gonna set up for next presenter.
yeah, I need the computer to go somewhere else.
Yeah, I'll give you computer to you.
Can you say that you is better than how to use the AI?
Uh,
Can you it's better than using AI?
yeah. So I can say, so I have reached kind of almost 50-60%. I have to yet to reach because so which I have shown here, the PDF file is able to extract even when you give the images, kind of scanning images. Not only if you give exactly the PDF file, you can give the including, you can add by intentionally, it would able to solve it.
But the rest is open.
Yeah,
You're right. It's an open air, not like an independent.
yeah, it's not in, yeah, it's not independent.
This guy keeps it right. Be aware of it. But we can help. We can help. That's our domain.
How could you help people to say, oh, right? Learning.
Sorry.
You figure it out.
Okay.
How did you know what models to use? How did you know even to get started?
So basically, how I did it, so in my previous time, I used to develop working on it, my background. So
Which program you are in here at
Python.
HU?
I'm ISIN.
ISIN. You're a master's or whatever?
Yeah, master.
That sounds good.
Okay. Sorry, people.
Gilberto, do you want to share your screen?
Yes, give me 1 second. I also apologize. I missed a couple of presentations. I was unfortunately in the wrong meeting because I think I had the incorrect link. Please let me know when you can see my screen. Anyway, give me 1 second. Okay, are you guys able to see my screen?
Just a minute, Gilbert. We're trying to access it from a different computer. I'm going to turn this off.
Sure.
Hello, can you hear us?
Yes, I can hear you, but there's some echo.
Go ahead.
Okay, so you can see my screen, right?
Yes.
Okay. So yeah, so thank you. And again, I'm sorry for missing the earlier presentations. I was unfortunately in the wrong meeting. I think I had the wrong Teams link. For those of you that don't know me, I am a computer science PhD student at HU under Professor Majid. My research is a lot about high performance computing, and in particular about random numbers generation. And what I wanted to talk about here today is a little bit about random number generation with C++. So this is my obligatory first slide. Why should you care? The short of it is, if you ever wrote code before for many things, for games, for machine learning, for simulations, for cryptography, you had to generate random numbers at some point. So this is something important that affects a lot of people in systems. Talking in particular about C++, the last time there was a major overhaul of functionality for generating random numbers with C++ was with C++ 11, which was published in 2011. Here is a quick overview of how it looks like currently. The main feature of the C++ library is that there is distinction between the operation for generating random data, and in the C++ library that's handled by what is called in the standard a random bit generator, something that generates uniformly distributed random data. And the other part is a random number distribution. What a random number distribution does is it transforms random data that's coming from a random bit generator into random data with the desired distribution, which might be something like normal distribution or uniform distribution, exponential distribution, whatever. The separation of concerns is very different from what you might be used to if you're more familiar with other programming languages like Python, Java, or something like Julia, where those things are kind of mixed together. I like the C++ design a little better. I am a fan of the design. I think it's powerful, flexible, and elegant. And it's very useful to be able to mix and match bit generators and random number distributions, and to mix different components from the standard library, and to mix different components with components from third-party libraries. And you can also write your own and have your own interacting with things from the standard library. So that's pretty powerful. Here's a quick example of how random bit generator usage looks like on C++ code. The first line here, I'm initializing a Marcin twister random bit generator. There is this warning here in a comment, don't do this. For the purpose of this slide here, I'm simplifying things a little bit, and I'm doing something that is actually pretty crappy to do. Never ever initialize a generator like this in code that matters. But again, for this example, just disregard that. I'll talk a little bit more about that in a few minutes. What this example illustrates is that you can infer useful information about the generator. In particular, here I'm printing the minimum and maximum value of the range, of the relevant range for this generator. And I'm also showing how to generate a random number. Basically, the generator has a function call operator overloaded, and you can use it as a function object to get the next random value. Here's how using a random number distribution looks like. Basically, you need to instantiate a random bit generator. Here, I'm instantiating a Marcin twister generator. The difference compared to the previous example is that here I'm using a 64-bit random bit generator. Here I'm creating a uniform real distribution, which is a distribution class for generating random numbers with a normal distribution. The real part is that you're generating floating point numbers, and in this particular case, 32-bit floating point numbers. And that's in the range 12.2 to 17.1. And here's how it looks like when you generate a value. So the distribution class, like the random bit generator class, has the function call operator overloaded. So you can use it as a function object. But when you call it, you need to pass to it the generator. So that's how it works. The distribution class by itself does not know how to get those random bits. So you need to pass to it a random bit generator. So it's going to use that random bit generator to get as many random bits as it needs. Okay. talking a little bit about the problems. So the main generator in the current C++ standard, and the only one that is really even considered really talking about, is the Marcin twistor generator, which is a generator that came up at first in the late 90s. I believe the paper is from 1998. This is the default in the current C++ standard, as I said. I say here, to be polite, underwhelming statistical quality. The generator is actually pretty crappy. It's pretty well known that you can make it fail well-known in statistical test suits like the Big Crush from test 201 pretty easily. So it's just a bad generator in terms of output. The other big problem with it is that it has a very large state. And because the state is very large, it's very hard to initialize that state properly. So it's very easy to initialize that state improperly and get messed up results, get a statistical bias because of that. It's also slow and hard to parallelize. In particular, you can't vectorize it. There is a CMD version of Marcin twistor, but that's a kind of a different beast and that has its own issues as well. And finally, the problems with the Marcin twistor generator are exacerbated by the C++ API that really makes it easy to shoot yourself in the foot. In particular, this line of code here in which I'm initializing the generator. This should just work. When you're talking about teaching C++ to new generations, you're doing CS 101 in college, this should just work and do the proper thing, initialize it properly. The fact that this does a horrible job at initializing the generator is very problematic. And finally, last thing about this, I just want to say, obviously this title here is a little slow, Marcin twistor is obsolete. This is not controversial. Anyone that has any real domain knowledge about this area knows that the Marcin twistor is obsolete. In fact, you could argue that it was obsolete 10 years ago, okay? C++ 26, that's the upcoming C++ standard, the next version of the C++ standard that's going to be published sometime probably in the middle of next year, that actually introduces a new generator, because the folks that deal with that are aware that the Marcin twistor just doesn't cut it anymore. It's introducing the Philux generator, which is a good generator. It improves into a lot in terms of a lot of those problems with Marcin twistor. Initialization, it's parallelized much more easily. It's also much faster. It has better statistical quality, so that's good. The issue that I have with the C++ 26 change is that you're just adding Philux. You're not adding other generators as well. And the problem with that is that when it comes to random number generators, there is no single generator that can be considered the best. They all have different trade-offs. So ideally, you would have a library in which you have real choice. And you can make a choice depending on your needs. You can make a choice going in a certain direction regarding those trade-offs. This is what Java did, as an example. Java revamped its functionality for generating random numbers a few years ago, and they introduced something that they considered like a good default, but they also introduced additional choices. With the C++ standard, you have one new choice, Philux, and that's it. And yeah, you can still choose the old ones, but the old ones are not even worth talking about. So in practice, you don't have a real choice there. So that's a problem. And there are many good generators to choose in the literature. I'm citing here some of those: LXM, PCG, Splitmix, Ushiro. They are all undoubtedly better choices than Marcin twistor. And again, it's not about me saying that, oh yeah, PCG is the best, or PCG is the worst, or Philux is the best. It's just that ideally you'd have multiple good choices of modern generators. So the initialization problem, as I said before, properly seeding a generator is hard. Improperly initializing it is very easy and common. I've seen that in well-known papers by well-known publishers in which they do a bad job. I've seen HU students doing presentations in class and doing the wrong thing. So it's very common for people to just mess up. But again, part of it is a fault with programming language that don't make it easier for you to do a better job with that. And the main takeaway that I want you to take from here is that basically the only real way to initialize well a generator is to fill up its state with completely random data that comes from a cryptographically secure generator, ideally getting entropy from the operating system. And that's easier to do if your generator has a smaller state. If your generator has a huge state like Mersenne Twister, that's very difficult to do it properly, but there are good modern generators that have very small states. Just as examples here, PCG has 128 bits state, so you can just choose two 64-bit integers to initialize it. Zoshiro has a 256 bits state, so you could just use four 64-bit integers to initialize it, and you would initialize it well. So again, another area in which Mersenne Twister really makes things harder. And again, the C++ API does not make this easier to deal with, and the next standard is not bringing any improvements in this dimension. So we can expect things to still be crappy just like today, at least for the next few years. Bulk generation. As you saw before in my code example, the current C++ API is really oriented towards generating single values. But ideally, you also have an API for generating multiple values at once. That's good for security because avoiding loops is always good because you can avoid out of bounds types of errors that unfortunately until very common in C++. And yes, you can say, oh, I'm smart, I'm never making those errors. Yeah, you are probably smart, but you can also have bad days. And we know from real life experience that those types of errors, when they happen, even if the chance of them happening is very, very small, the consequences can be catastrophic. So as someone that cares about security, I just have to mention this. This is an advantage of a bulk generation API. And of course, the main flaw for a bulk generation API to most people is performance and parallelization. The idea that you can provide a function that just does the hard work for you of parallelizing and making a generation maybe as fast as you want. And the third point is also kind of important. Ideally, a bulk generation API should prefer free functions versus member functions of classes. This is a contrast between C++ and other programming languages. This is not how I would recommend things to be done in a language like Python, but C++ is different. I also mentioned this because in the past there have been proposals to change the C++ standard, and those proposals were blocked. And partly they were blocked because they were basically trying to implement something like a Java API in the C++ world. Okay. Bulk generation example. This is how it's going to look like on once C++26 is available. There's going to be this generate random function, and basically to call it, you pass to it the container that you want to fill up. You pass to it a random bit generator and a random number distribution, then you're done. So that's going to make things a lot faster. Just give me one more minute, please. The last thing that I want to say is that generate random improves things. It's good to have bulk API. It's good to have a good bulk API that is consistent with the rest of the C++ standard library, but that lacks in many regards. In particular, there's no support for execution policies, so you cannot have parallelized overload. So in fact, you will not be getting with C++26 that's fast overload that can do parallelization for you. And also there are other big improvements coming to C++26, things like context, CMD support, stud execution, that is a whole new framework for concurrency. There are many missed opportunities there. All those things could be taken advantage of by a more modern C++ API for generating random numbers. Unfortunately, none of these changes are coming for C++26. So yeah, that's it. Thank you. And let me know if you have any questions.
We will have time for one question. The rest of you, if you want to type in the chat.
Yeah, sure. Please let me know.
So I have a very simple question.
What is the question?
Okay. Okay, so I have a verification. So you introduced the bad scope on random number generation. In the case, why just to we use just to Java's random number generation?
Oh, that is a good question. I
Sure.
think it's some
I
it's some
believe the random number generation is okay in Java or other programming languages. Then why not? We just to use the random number generation from other programming languages.
yeah, I think that without trying to spark a debate that could take hours, I think many people could argue that they just want to use C++ because they think that C++ is better. I'm one of those people, by the way. But as I said, this is a debate that could go for hours. I don't want to use Java. I don't think anyone should really bother with Java that much in 2025. But we could debate about that for hours. So Java has a lot of issues. The fact that the Java API for random numbers is a little bit better is not a justification for just switching to Java. And again, in the real world, in many situations, it might be impossible to do that. Many times companies have legacy code bases that go back decades, and it would take them millions, maybe even billions of dollars to rewrite those code bases in another language. So in the real world, in many situations, the the answer to the question, why not just use a different programming language? It's just not feasible to do that.
Thank you for your answer. Gilberto, if anyone have more questions, you can type in the chat and then he can respond you that way. And then we'll have our next presenter, I think is Xuan Liang. The topic, well, about optimizing data format detection for data visualization. I can share the screen here, or if you have your slides, you can go ahead as well, so that way you can control your slides yourself. Maybe do you want to do that?
Hello. Hi. Yes, I have the slide ready. I can share my screen.
Yeah, go ahead.
One moment. Hello. Hi. Can you see my screen?
Yep, looks good. Go ahead.
Okay. So hi, I'm Zishan. So today I will introduce our work on the automating date format for detection for data visualization, which will be presented also at the AMLDS conference. So data preparation is so in the next 15 minutes I will introduce our I will introduce our work according to this table of contents. First is we have introduction. Data preparation is a major bottleneck in an analysis. So imagine if you are exploring your favorite BI tools like Tableau, Power BI, and you just drop in a fresh CSV file. You expect it to quickly slice like sales by month, but instead you see an empty chart or garbled axis labels because your date column has mixed formats. Some rows are like just different formats, like maybe dash, like months in front or date in front, or maybe even text like July for something like that. In fact, so studies show that 3.3% of data workflows like they store on date parsing alone, and that error cascades because failed queries would lead to misleading dashboards and hours of manual data wrangling. So this is like a real dashboard where mismatched formats render timelines useless. So analysts end up looping between spreadsheets and code, breaking the flow of insights. So that's the problem that we are trying to solve, making date parsing disappear from analysts' worry list. So the problem currently is a lot of the high variability of the date. They appear in countless conventions, and it involves lots of manual overhead. Crafting custom parsing rules or regular expressions is tedious and brittle. A tiny locale shift, it can break everything. So if we introduce some downstream costs, and a single misparsed state propagates through SQL queries, BI2 calculations, and ultimately it would change decisions, affect decisions. So we need a universal automatic method that can ingest any data stream, infer its format, and convert it correctly without asking the users. So the objective would be achieve full automation and no dropdowns or user hints, just label this column as date and let the system do the rest to achieve high accuracy, aiming for 95 plus parsing correctness on the messy real world data, and have a interactive performance to achieve sub 5 millisecond per value, so dashboards remain snappy, and it has easy integration that can fit into BI tools, database, and ETL pipelines, and handling ambiguity to be robust to partial strings, locale settings, and text-rich inputs. So meeting all this means, we design a dual algorithm architecture. I'll explain in detail later. So the overview for this, for our methodology is combine two approaches in parallel. The first one is the minimum description length. It is optimized for speed. It is fast, rule-based, better for structured numeric patterns. And the other method is NLP-based. It's grammar-driven, probabilistic. It's better at ambiguous or text-heavy days. It can handle ambiguity better and diverse linguistic expressions. So both of these outputs in the standard date format, which is called ICU, International Components for Unicode, this date format language. So the downstreams, we can have a single standardized format stream. And we train and validated over 60,000 real-world spreadsheet columns, iterating on error cases to refine both methods, and then cross-validate MDL method against the NLP to gain confidence in the format and catch any edge cases early. So the first one is the MDL algorithm. What it does is basically seeks the simplest format that explains the samples. So think data compression applied to date patterns. So here is how it works. So it first does the pattern extraction. So it identifies candidate tokens, like digits, separators, month names. So then it do the redundancy pruning. It drops the repetitive or irrelevant patterns to shrink the search space, and then it does a scoring on the locale where does the locale where scoring. It ranked all the candidates by regional likelihood. For example, in Europe, 31/12 would outweighs 12/31, something like that. So, and then does the parallel evaluation. We test thousands of candidates in parallel, achieving 620,000 values every second, every core. And so for the highlight of the metric, so on the validation set, the MDL passed about 95% of the records. So averaging 2.5 milliseconds every test. So it is ideal for numeric heavy and regularly structured, a more structured format input. But for those that are less structured, we rely on the NLP-based algorithm, which use a context-free grammar and context-free grammar with the weight rules, PCFG, probabilistic context-free grammar, and a CYK parser, so that it can handle ambiguity. So for example, discriminate 5/6/2020 as a month day as versus date month using probabilistics, and it handles the text-based phrases, like phrases. It can parse something like spring 2000 DEC3, those texture input. So even like quarter text like Q3, and also partial days. It fills in missing pieces with some defaults or flags for user feedback, and it also does the grammar corrections. It tolerates extra spaces, unusual punctuations, and capitalization, those irregular data. So because of the parser, complexity is bigger of n cube. It is slower, so it takes around 0.9 seconds to rank the parse trees for a column. But it covers those cases that MDL cannot handle. So, and in validation, it has about like 84.1% accuracy on those messy columns. And in terms of the evaluation, the data set includes about 30,000 training and 31,000 for validation records. Those are assembled from user contributed spreadsheets in multiple languages. So we manually review about 850 challenging cases. So the key results here, the MDL method achieved 95% correct parsing with 2.5 milliseconds every test. And NLP achieved 84% pattern detection accuracy, and with the flexible grammar support, and with the cross validation shows the two methods agrees on the dominant format about 98% of the time, letting us flag the disagreements for human review. So this number shows both the speed and robustness. So each algorithm covering the other's blind spots. And then we built production grade parser, MDL parser in C++ for high throughput environment, NLP parser in Python with plans to port to C++ for acceleration, and integration. Some integration points here include we integrate with the visualization tools like Tableau, Power BI. So no menu format dialogues. Also integrate with the database, including Postgres, MySQL, Oracle, etc., and also ELT data pipelines. Some features include the features include a user feedback loop, so the system learns preferred patterns over time, and locale-aware real-time batch processing, and to keep the dashboards interactive. Of course, there's some limitations in this work. So, for example, it is dependent on the ICU format. So ICU doesn't cover some weird formats like for example Roman numeral, those kind of formats, and NLP performance is not that great because in terms of the latency, like the time complexity, because of the parsing is lower. It will limit some real-time use in the current situation, current form, and for some columns they are mixed format, so it is hard to deal with when a single column makes dozens of patterns. But that happens. Doesn't happen that often. And also there's some locale mismatch. So some wrong locale and inference that they still causes some mispasses. And for NLP based, the algorithm for messy data, there's still requirement that we still need grammar tuning. The NLP grammar requires domain experts to extent. So addressing this will be key for a broader adaptation. For the future work would be like multiple format detection, dynamically switch formats within a column. Like I said, that may be mixed inside one single column, and also encode a numeric date, and historical regional formats, adding support for ordinal format, Roman number format, like archival customs, and to improve the performance. So to rewrite the parser, NLP parser, to make it faster for more real-time scenario, and also adapting like a hybrid models. We can combine like MDL, NLP, and maybe also machine learning with reinforcement from the user correction to adapt over time. So yeah, I think that's to sum up, we present like two complementary algorithm, MDL for fast structured recognition, and NLP for flexibility, ambiguous, and linguistic format. So with the 95% and 48% accuracy respectively, with a combined match rate of like 98%, delivered a performance product ready, production ready components integrated with other BI tools, databases, and data pipelines. And that's it, I think. Yeah, thank you. If you have any questions,
Good
again,
presentation. There's a question in the chat if you want to address that later. Do we have any question from the audience? Yeah, there are a few feedback in the chat. For our next presenter, I think it's Niharika. If you want to set up. Yes, yeah. We have one question for you while we are setting up here. Yeah, go ahead.
Okay, you mentioned the accuracy rate of MDL is 95.1%, and the accuracy rate of NLP is 84.1%. But how you can get the accuracy rate of combined method 97.9%? It's quite high if you combine both. So how did you get this accuracy rate 97.9% for the combined method?
Did you hear the question, Zixuan?
Oh, hi. Yes, I can hear the question. So So that the MDL 95% is in the rate at which the MDL parser by itself correctly parsing in the validation set, and the NLP's number 84% is by itself using NLP, and 97.9 isn't a new parser accuracy. It's the agreement rate between the two methods when they both infer a format for the same column. So in other words, like in 98% of the columns, NDL and NLP independently converge on the same format string.
So yeah, if you want to address those questions in the chat, go ahead.
So the chat is from Professor O'Hara. Okay. Based on what percent of the out there is messy and
Oh,
incorrect?
you can just respond in the chat. We're gonna have our next presenter go ahead. So thank you,
Okay.
Sid.
Yeah.
So Niharika, if you're ready, you can go ahead. I think your topic is something about Parkinson's disease. Very interesting. Go ahead.
Yes. Thank you, Dr. Lu. So good morning, everyone. I hope you can hear me. So today's topic, can you hear me? Oh, okay, good. Okay, sorry. Okay. So my topic is non-clinical preventive measures of Parkinson's disease, identifying key lifestyle, demographic, and environmental factors. So this is the basic outline: background, problem statement, research questions, hypothesis, literature review, data, methods and results, implications and findings. So what exactly is the Parkinson's disease? It's in a simple English, simple basic English, it's like group of specific brain cells that those producing the dopamine slowly die off. So this, the dying of these particular neurons so leads to the disruption of communication in the brain, leading to symptoms, both motor and non-motor symptoms. The motor symptoms include tremors, rigidity, bradykinesia, and postural instability. In addition to the non-motor symptoms such as sleep disturbances, fatigue, constipation, and depression. So why exactly are we trying to study this? There's been a lot of studies on the Parkinson's disease, but most of the studies were on the cellular level. So my study mainly focuses on the non-clinical aspects of it. So there is an urgency here because the prevalence has been doubled since in the last 25 years. As we can see the stats here in 2019, there are around like 8.5 million globally affected individuals. And there's also 5.8 million disability adjusted life years. And that caused like 329,000 deaths nearly as per the World Health Organization. So it's been said that Parkinson's disease was mainly seen in the old age, but there's also cases that were diagnosed before age 50, that's 5 to 10%. Only 15 to 25% of the cases were related to familial connections, that is, they have the hereditary, but the remaining 75% were exogenous factors. So this is what this study is focused on. So there's also a future projection, like there will be like 13 million, the number would be increased by 2040. So we can see the urgency here. So the problem statement is what to explore these exogenous factors, how to reduce, can we find to reduce the risk of Parkinson's disease by addressing the lifestyle factors, environmental exposures, or promoting early interventions. We can significantly mitigate the burden on the PD individuals, on the caregivers, and also the global healthcare systems. So the literature review has shown that most of the males were affected, and also they are more likely, like 1.6 times more likely to develop the Parkinson's disease. And the underlying theory was that because they are more exposed to the occupational exposures like pesticides, something like that. But the studies that were conducted in the Japan shown that women are more affected with the Parkinson's disease because they are more likely to work in the fields and exposure to the pesticides. And Mediterranean diet, caffeine, and vigorous exercises were known to be like a protective factors. But there are still a lot of gaps in the literature review. As we can see, there is a very little scant literature review on the public awareness and also the public perceptions of Parkinson's disease varied across the cultures and regions. There's been a lot of studies on the etiology of PD, but it's very difficult to find exact cause in the most of the patients because of the various, even though there is various genetic etiology has been identified, the non-genetical factors and the preventive measures were studied very little. So here comes the research question. Do environmental risk factors differ significantly between Parkinson's disease persons and non-Parkinson's disease individuals? So the main objectives were to identify any key environmental risk factors and the interventions that has been shown to reduce the risk of PD and evaluate the effectiveness of those identified preventive strategies. So I have a lot of variables here, like 24 predictor variables. So I divided them into 4 different factors for the easy understanding, like demographic and socioeconomic factors, lifestyle and behavioral factors, health-related and medical history factors, environmental and occupational exposure factors. So the hypothesis was built on the 4 different kind of factors too. So my main data source is from Fox Insight. So this is a Michael J. Fox. He's a very famous Canadian actor. He got Parkinson's disease at very early stages in his life, around 29, age of 29. So he built a foundation to do research on the Parkinson's disease and fund the study. So I obtained this Fox Insight data source from them. And this is the clinical database, FoxDen. And they have conducted a one-time environmental exposure questionnaire. And the timeline is like October 2017 to 2019. The age is 18 years and older. So the basic data set included all the demographic information and the one-time exposure questionnaire related to all the lifestyle and all the other factors. So I merged all those 11 additional data sets of responses to the basic data set. So the traditional data cleaning steps involve removing all the unknowns, prefer not to say responses, and I recoded certain variables for consistency and analysis. And there are like lifestyle factors, especially the physical activity, sleep, and the residential variables. There's a lot of information, data was collected throughout the participant's lifetime. So I have recoded them based on the mode for the simplification of the data. So this study is a cross-sectional study, and the sample size was around 1,198 participants. As you can see, there's an imbalance between 2 data sets, 2 groups. The PD individuals were more when compared to non-PD individuals. So the variables analyzed were age, BMI, race, all the income, educational, employment, pesticides, occupation. And the statistical analysis I used was Mann-Whitney test for medians because the age, BMI were skewed, and the chi-square test for categorical variables. I did logistic regression and used backward step pseudo R-square selection, as I have a lot of predictor variables. And I used VIF to check if there is any multicollinearity. To address the imbalance between the data sets, I use SMOT and also random forest classifier to deal with that. As you can see, the results here, age and BMI are skewed, but as we can see, the males were more predominant in the PD area, and the females were more predominant in non-Parkinson's disease. So the bivariate results were shown that Parkinson's disease group individuals were older, and the results were significant. And also the occupational history shown that individuals with the PD group are more likely to have served in military, and they have a high pesticide exposure too. And the more they lived more, the rural people, the PD individuals were, they lived in the rural areas more. Coming to the lifestyle factors, they have the less vigorous physical activity was observed in the PD group. So the key predictors here were age, gender, and pesticide exposure were observed in the Parkinson's disease. If you're older and male and exposed to pesticides, you are highly likely associated to develop the Parkinson's disease in the future. So I have done the SMART analysis and the random classifier for the accuracy. As you can see here, before the logistic regression is 87, even though it is 87% accuracy, because of the imbalance, I used the SMART analysis. The accuracy gone to 80%, and later I used random classifier, and the accuracy increased a little bit, 84%, and it also predicted the PD cases are better in this model. So the implications of these findings were targeted in interventions. Understanding the role of age, gender, and environmental exposures could help in identifying the high-risk individuals. And also the public strategies focusing on reducing occupational and exposures and promoting the physical activity and addressing the socioeconomic factors could help in preventing or reducing the risk of developing Parkinson's disease. The future recommendation would be to explore the mechanisms underlying these associations and how they may interact with the genetical and clinical factors. Thank you. Any questions?
I have a
Thank you.
question. Can you hear
I
me?
have one question here.
Yes, please go ahead.
Go ahead.
Oh,
See.
okay. So the variables include age, occupation, gender, something. So those are all given, right? So you cannot change genders, you cannot change ages, you cannot change
Yeah.
occupations. So how you can prevent the Parkinson's disease with this analysis?
So when I say occupation, if there is a pesticide exposure in the area, so if we can educate the individuals about the early exposure, and the public health strategies such as using the masks that could reduce the exposure of the pesticides, that would help. I know the age and everything is not in our hands, but still, if we have a knowledge about this, you'll be like taking good care of like food and also the physical activity aspect of it. So see, the Michael J. Fox, I know he's an actor, but he got his Parkinson's disease at the very early ages, which is very rare. It's like 29 years. But due to his physical activity and other factors, like he could able to live on I think currently his age is 67. Because of that, so he wants to bring that awareness to the individuals, I believe. Yeah. Did I answer the question?
Yes, thank you. We have a professor online. I think, let's see, have a question. Do you want to go ahead, ask Professor Shanta?
Yes, thank you so much. Thank you for your lovely presentation, and it was very informative. I just have a question that you said that 3 factors were key there. One of them was
Mhm.
age, and another was
Gender.
gender, and then the
Yeah.
last one is environmental exposure. So I was just wondering, like the other key factors which that comes to our mind, are like the lifestyle and also genetic factors. Did you study any contrast, like how do those key factors play a role on top of these three? Did you do any comparative study, or do you think there is a scope for doing those ones?
Uh, uh, Thanks for asking. That's a very good question, Dr. Sandor. So I think the data set is very huge, and I don't have enough time to check the genetical factors too. But the future recommendation would be that, because I think this is one of the good data set that they have been gathering the data, especially on the environmental and exposure. It span across the world. So I think it would be nice to see someone picks this up and compare it with the genetic factors too. I would definitely suggest that.
Yeah, thank you so much. Yeah.
Thank you. Yeah.
Awesome. If we don't have any questions from the audience, could Shatyam, would you like to share your screen? I've also got some comments in the chat, if you want to review that. Can you hear me? Well, we will wait for the next presenter to get ready. Shayam, are you here?
Yeah, I'm here. I'm here. Dear.
Oh, okay. Do you want me to
Uh,
share
no.
the slides, or can you share your slides?
I can let
Okay,
me.
yeah, go ahead. Thank you.
One sec. I'm having. Where is my Teams? Okay, right there. Presenter view. One sec. I'll share my screen. Okay. Do you see my screen?
It's blank.
Interesting. Give me one sec.
Yep, we see it now.
Okay, perfect. Perfect. All right. So thank you all for letting me present this topic today, and giving me an opportunity to share knowledge with everybody here. Um, this is Sham Nalwade here. I'm a PhD student in computational science, working under Dr. Majid Shalan and Dr. Mike, trying to get my hands wet into this interesting topic for photonics computing, especially focusing on optimizing the two components, micro ring resonators and the waveguides. Um, I'll jump right on to the introduction. Um, the basically I know some of the folks here who know the photonics, and some of them might be wondering what is photonics computing. Photonics computing is basically a computing through a light, because the current computing architectures runs through electrons, through electricity. So the next generation of computing is going to be photonics, because light is considered to be more faster compared to electronics. And then, like I said, I will be focusing only on the micro ring resonators and the waveguides optimization, because those are the core components in photonics. The reason why we
are moving to photonics computing is because we have hit a dead end with the current von Neumann electronic architecture, because there are so many bottlenecks that are causing issues, especially in the applications that needs parallel processing or high performance computing, or the applications that needs to process tons of data. That's one that's that there are some reasons that I just mentioned is why we are moving to photonics computing. And not only to resolve those issues, but also to support the future applications, right? Because now we have this wave going on, shifting everything from on-prem to cloud, and then cloud to AI and ML based architectures. So it this photonic is also going to help um, uh, compatibility in terms of compatibility against those future applications as well. Um, and this is just for information, like whoever is new to this topic, this is how the architecture of photonic computing looks like. Um, this is a micro ring resonator, kind of a ring that's round. It doesn't need to be round, it can be oval and other shapes as well. But that's the standard way to see it. And then this is the waveguide. The waveguide helps you channel the light or guide the light through various components on the photonic integrated circuits. And the micro ring resonators um, um, helps you filter the light, right? Because there could be an intensity where the light is low or high. So in order to have smooth transmissions between the components, you would need to have a, a stagnant light passing through the components. And the reason that I am doing this research is von Neumann bottlenecks that we just talked about, Moore's law limitations, where the Moore's law says that there is transistors, which are the core parts for processing, gonna double for every 18 to 24 months. It was doubling, but now we hit at a point where we cannot add more transistors to make it more faster. So that's the reason now we are these are some of the reasons that I have started my research. Of course, photonic computing does provide um, more energy efficient system, which costs less, and it has more computational speed compared to the current electronic architecture. I've already covered the focus area. These are the two components that I want to focus on. And the reason I want to focus on these two components are listed in here. The first one is fabrication tolerance, because with the initial round of analysis that I did with Synopsys tool that's been provided by HU, still a lot of simulation rounds has to be done. But the basic things that I understood is even there is a small variations in ring dimensions or changes in waveguides or changes in coupling or the distance between the waveguide and the ring resonator, or the bus guides and the ring resonator, can cause a lot of resonance, which basically means causing an inconsistency across the chip through various components, which means it wouldn't be effective in terms of processing. And then there is a coupling control. This has to be very precise because when the coupling happens between the ring resonator and the waveguide, it's not important to use only the bus waveguide. There are other waveguides that I'm going to use in my simulation rounds for variations of testing to achieve the most precise way of coupling between the ring resonator and the waveguide. Um, the reason why I'm doing research, because the issue is the overcoupling or undercoupling, which means the light passing through waveguides on resonators. If it's over or under, it's gonna lose its quality and signal transmission. The third main reason is the free spectral range. This is tied to the micro ring resonator, because the smaller the FSR, the more the overlap is going to happen um, um, on the light that's passing through, which basically limits the multiplexing capability, which means we cannot distribute the waveguides, which is needed for an applications like AI and parallel processing based applications where we need to process parallel things at the same time. That is something that's limited through a small FSR. And that's the issue. So if we resolve this, even it's gonna bump up that parallel processing power for the AI based applications or any application that runs on parallel processing ability. And the way I'm gonna integrate my research to do practical analysis on this two components is using different tools and technologies, Synopsys and Nazca. These are the simulation tools that I'll be using, where I'm going to create different designs based on micro ring resonators or waveguides, passing different parameters to understand the simulation results and to improve the performance of those simulation design. Not only that, but I will be um, um, considering the fabrication error simulation, because sometimes what happens is you do a simulation with certain parameters, but when you go to fabrication of the chip, the results vary. So in order to um, um, in order to keep those fabrication changes in mind, we have to take that assumption and put it into the simulation models when presenting. Um, and design for tolerance, where we're gonna design the simulation in a way where we are expecting the results. Uh, like if I'm passing A and I'm expecting B, it has to be B. So we're gonna design the simulation that way, considering the output of the simulation design. Um, and then Python, C, C++, and NumPy. Python I'll be using for automating tasks once I have the simulation design ready, and if I want to automate some of the test results, some of the parameters that are going to the simulation design, and storing the outputs somewhere, all these types of tasks, I'll be using Python for it. And NumPy is where I'm going to use for data analysis, because when I run through hundreds and hundreds of simulations through variations, through different designs, um, I will be using NumPy on that data set to do an analysis to understand the output performance. Other than that, I might be taking a help on the ML-based algorithms, because I don't want to develop the algorithms itself when they are already available in the market. Um, Companies like Light Matter, they are using, they are kind of in the same domain. So they are using an application called EDM, which provides an ML-based algorithms, which also includes the neural network algorithms as well, that they are currently using for their research on improving the photonics. So I'll be using things like that. Those are already existed that can help me on my way to achieve the best design possible for photonics computing. That's all I have. Thank you so much for allowing me to present. And I'm open for any questions if you have.
Thank you for your presentation. Do we have any questions from the audience here or online? Yeah, we have a questions here first. Yeah, go ahead.
Okay, you introduced some benefit of using photonic computing. Could you introduce some downsides of using photonic computing?
Sure, sure. That's a good question because nobody thinks about that, right? Even when we started with electronics, we thought, electronics is going to be um, the best architecture, but now here we are um, dealing with it. Similarly, photonics has its own set of integration issues. For example, um, um, even nobody found out that there is a fully integrated photonic system yet. um, so which means we might be having an hybrid integrated system um, because not all the components can be converted to photonic for now with whatever the research we have. The challenge will be, or the downsize will be, it's gonna be costly for sure. In terms of computation, um, it's definitely gonna provide efficiency, but the system is gonna have a lot of complexity. Did I answer that question, or am I?
So, hi, Shyam. This is Mike Shaheen. I'm Shyam's advisor on this. I can add to this. Packaging is a big issue for this. So, if you want to use photonic systems, you need to develop the packaging aspect of this as well. And that's not addressed in Shyam's work. This is going to be done in separate work as well. So, packaging is a big issue for integrating the discrete components of photonics together on a single chip.
Thank you, Dr. Mike. Yeah, and that's gonna happen like after fabrication, right? Because right now we are in design and simulation. Once that's done, we will be moving to testing and fabrication, and then the last part is gonna be for packaging, and that's what Dr. Mike was talking about. Thank you.
Thank you for your answers. I think we have audience online have question too. So Emma, do you want to ask your question? Go ahead.
Thank, thank you, Jan. For the presentation, okay, I have question. So as you mentioned, there are plenty available machine learning. There are plenty machine learning models that you said. A framework also has been designed. So would you like to develop your own framework for your research, or you're going to use exist one, and how much they can they help you to solve the problem otherwise? And the question is, what kind of data that you're going to use for the machine learning?
Yeah, thank you for your question. So I'm definitely gonna use, if there's the best tool out there, which I did some research, and the one thing I found, and not all of the companies put their research in the right location. So I went through this company called Light Matter. They're doing the similar work from a long time. They did mention their resources in there, and they did say that they use EDM tool for machine learning. So I definitely don't want to, recreate an ML algorithm or an ML model itself to to uh, to do analysis or any kind of testing. I would like to use an existing ones, which I think is the best fit for me to do the analysis and the simulation testing. When it comes to the data, um, I will be using, I haven't thought about it yet because right now I'm just in simulation phase. But when we goes to testing, I would definitely would like to use a data set that is tied to the photonics. That way, the nature of data is going to be the same. So I can test the existing ML model based on the data for testing.
Yep. The following question, as you mentioned, sorry, we have some echoes. you said Light Matter. Light Matter, the company that you are pre-existing model that you're going to use, and it's open source or paid versions.
The EDM, I think it's a paid version. I haven't tried that yet.
Okay.
But let me put a link in the chat. That way you would know. But I think it's a paid version.
Yeah.
Yeah, I don't think it's definitely not a free version for sure. I wish it could, but it's not. Let me put
And
that link in the
last
chat.
question. This is going to use the machine learning model. It's classification models or regression or multi-class classification.
I'm sorry, you're echoing out. Could you please repeat that question?
Yeah, my question, last question, like, you're going to use, how you can say this is a, how you can define this problem statement, like it's classification or regression or multi-class classification.
Oh, it's going to be a regression because it's not just one round of simulation and testing, right? I have to keep on doing a regression testing until I find the results that I'm expecting.
Yeah. Thank you.
Thank you.
Thank you for presentation and answering all the questions. Our next presenter, Nathan, would you like to set up?
Hello, can you guys hear me? For sure.
Yeah. The topic will about AI-driven. Oh, it's the similar topics earlier for HPC applications. So yeah, go ahead if you're ready.
Sure. I think that is kind of like, okay, now it's better. Yeah. So this topic is about AI-driven photonic inverse designed for HPC application. So that's pretty much a continuation of my colleague Shyam actually had presented. I'm gonna try to break it down and provide more input, and I hope that will be helpful. So yeah, I'm gonna move from scratch. So what is silicon photonics? So basically, it's a technology platform that integrates optical components onto a silicon chip, enable light-based information process at micro and nano scale. With key feature of it is the material that we utilize for it. So we utilize the silicon the same way with electronics. We use a silicon, and we as well do it kind of inspired as well of the mature CMOS manufacturing process as it does as well for the electronics. And its functionality, it guides, modulates, and detects light within a chip scale devices. Mostly, of course, it's been used for a wide range of applications, but most often at this point is for the sensors, the way that it detects the light for the radar and applications into the same area. As well is used as well for data center interconnects, high-speed optical communications. Sensors I was mentioned, like biomedical environment sensors, and as well it's now an emerging technology as it emerged with the quantum and neuromorphic computing systems. And for its advantages, as well as said, is a high bandwidth, low latency communication, the low cost mass production, and as well the compatibility with existing electronic circuits. So we can have a hybrid approach using both electronics and photonics to have an application. Why it matters? So silicon photonics underpins the growing demand for faster, smaller, and more energy efficient photonic device, making it efficient for the future innovations. So here is kind of like a small demo of an optical waveguide, a wire of light. So how that this is a waveguide, I can put that into play. So this is a waveguide. So we can think about that like the equivalent of a simple wire in electronics. In the photonics, we're going to have a waveguide. And as you can see, this is a light, right? And usually when you see the blue is the electric field and the red is the magnetic field. And this is how it propagates through the waveguide. In electronics, it's simple, just a wire, copper wire, where electronics actually travel through. And in this actually research, because we're using an AI to detect what is the best dimension, the length or the width of this whole waveguide to suit our applications, to have more powerful wavelength at the end that we can try to minimize losses, right? That's why we now come up with this research with a AI-driven inverse design. So basically, we're gonna use an AI to then at the end is gonna help us to tell us what is the best parameters to take in for our suitable application. Um, yeah. So and as well as just seeing that uh, uh, diagram. So this is the waveguide, right? And this is where the light travels in this core area. Then we have this two sections above and underneath. So this is the cladding. This is actually isolator's material, right? And that's what confines the light to travel through this core to not get out from this waveguide, etc. So this is the basic note to take. So waveguide is a path where the lights travel through, and it's been isolated with two materials. The way we can confine the light within that waveguide. So this is the basic a reflection, because as we know, light reflect on materials. So it keep it bonding. It travels towards the bottom, and since this material N1 is an isolator, it's gonna bounce back and keep traveling through the waveguide. Yeah, so we have as well different shapes of waveguide, and they all been used in different purposes, right? So we have this most common buried waveguide. As you can see, the dark one is the core, and this is how the light travels through. Then we have a different waveguides, like diffuse waveguides, the ridge waveguide, right? So the core is this dark one. We have all these different waveguides, and that's for different applications. It can be for sensors, different type of material sensing, for example. So as well, check on the shape, the size, the material matters when it comes to waveguide, and this is what also about in general. Now for photonic chip, to have an idea, so how this is how it looks like, right? As you can see, they're all about paths, and all this is waveguides, right? So they all in different shapes. We even have like a ring resonator. As you can see, they're not even interconnected. So basically, they interact with an electromagnetic field, right? So the take on in here in the silicon photonic chip, uh, it's all about the shape, the size, and as well the distance between all elements, right? Because they're waves, so they interact between each other, right? Yeah, so to summarize, so photonics layouts a central role in technologies such as communication, imaging, sensing, computing. Design a high-performance photonic device requires a precise control of light, matter, direction. However, the conventional method like parameters, sweep, and evolutionary algorithms are computationally intensive, and scale poorly as device complexity increases. So now the challenge is it's not just about the approach, but as well is to how you can set up the parameters, the properties of your chip, right, of the waveguides and the ring. This is the biggest challenge. And now with deep learning, with this recent advances, we have this particular model. It's called Deep ONNET, offer a transmosive alternative by learning mapping between design parameters and electromagnetic responses. Deep learning and enables rapid, scalable inverse design, unlocking new possibilities for the new generation of photonic devices. So this is just a background for the equations. So light is just pretty much a electromagnetic wave, right? So we solve those equations by that they are governed by Maxwell equations. These equations describe how electric and magnetic fields interact in space and time, forming the foundation of optical physics. And in most realistic photonic devices, so analytical solution to Maxwell equation are infeasible due to complex geometric and material. Instead, we use methodologies such as the FTDT and FEM, which is a finite element method, and BEM are used to approximate the electromagnetic behavior, right? So understanding and solving Maxwell equations accurately is crucial for designing photonic devices that meet performance specifications. However, full wave simulation are computationally intensive and motivating the need for faster, more scalable alternative like deep operator learning. So this is quick overview of what is an FDDT because I used it for an experiment. So basically, this is the light, right? So what we do is we discretize this whole wave into a shape and size, and we're trying to run a couple of mathematical methodologies like the partial diffusion, the PDE, to come up with a result. So this pretty much what FDD is. And we have as well FUM, which is pretty much similar, but is more about meshing. It's not only used in photonics, it's used in any is CFD as well, right? To calculate how the heat is gonna interact with the material. So these methodologies are computational simulations for physics behavior in general, but it's we used widely in the photonics. So here we see what is the FDD, which is sample grid based but memory intensive for fine structure. The FEM, we've seen it, which is a flexible with the complex geometries but computationally heavier. So this one, the downside with the FEM is computationally heavier, but it's good for complex geometries. Usually we use it in softwares like ANSYS. Those are specific softwares that interact with desktop and interact with all the CPUs. So, but for using just a sample application in Python, for example, we use the FTT. So now, what is the inverse design, right? What is deep learning in photonics for inverse design? So the traditional optimization method for photonic design are limited by computational speed and scalability. Deep learning offers a new paradigm by learning complex mapping between design parameters and device responses. So we have this early approach, such as a physics-informed neural network, we call the PIN, and generative the GAN as well. So demonstrated the potential of machine learning for solving forward and inverse problems in optics. However, scaling these methods to large design space remains challenging. And operator learning framework like DeepONet that I used actually for my project represents a major breakthrough. Rather than approximating solutions point by point, DeepONet learns entire operators, enabling fast and generalizable prediction across a wide range of photonic structures. Evolution of inverse design. Just to summarize, so it started by just using deep learning, and then we learned that that's not sufficient to solve a physical problem. So usually it's a what is an inverse design model? It's a deep learning that is working with the PD and OD functions to provide and that interacts with this EM solvers to come up with a suitable output. So that's what this inverse design methods do. Yeah, so the methodologies, as we just said, is an image solver such as the FDD, FM, and BM, and we use those to calculate all the computation, and then we use DeepONet to learn the mapping between design parameters and EM fields outputs. So what is DeepONet architecture? DeepONet is designed to learn mapping between function space, making it ideal for predicting electromagnetics field distributions from photonic device parameters. It consists of two main network, branch network and trunk network, which the first one processes the device design parameters, waveguide, geometry, material properties into the talent representation. And the other network process the spatial coordinates within the device position to capture the field variation across the space. So the output of the two networks are combined through an inner product, producing the final prediction of the electromagnetic field at each spatial point. Pretty much how it works. The input, and this is output. But here we have the differential equations, which is the ODE or partial different equation solvers. So the input is this is we get it by the AM solver like FDDT. Then we have an output, give us the result after running all through all these two branches. So to be very to actually summarize, so what is deep learning via the physics informed deep learning, right? So the core idea here, the standard deep learning, learn patterns from a large data set, where the physics informed deep learning embedded physics laws like Maxwell and Navier-Stokes. So to just summarize, deep learning learn from large data set. We train and test, and we train and we come up with a model. However, this physics informed deep learnings they use the physical laws instead, right? They're designed for the physical problems in general. So, for example, as well, for deep learning, require large label data set. However, with the physical informed deep learning, can work with a few data points in, if the physics are known, basically. So the application, so deep learning is more for image classification, NLP, speech recognition, but depends they for solving differential equations, modeling physical systems, and scientific computing. So to summarize, this physical informed, they mostly are used for physical problems if the physics laws are known. So how deep learning or physics informed learning help find suitable design parameters? So first, as we mentioned, we generate EM simulation like FDT or EM. Then we use a deep ONNet to learn the inverse mapping implicitly. It predicts what the field will look like for any new set of design parameters. Once trained, you can quickly evaluate thousands of candidate parameters without running new expensive simulation. So all what we're doing right now is to avoid all those expensive simulation and avoid all those mistakes, because the biggest thing is to tap out a chip through the factory, the foundry, and then find out that is malfunctioning. So all what is this model is going to help us to avoid all these mistakes. And this is by performing repeat optimization. It uses the gradient descent, the same like deep learning. Randomly search across the design space much faster and explore much larger, higher dimensional parameter space than traditional methods. For data generation, right? So to simplify, is for deep learning, we just get data, we train it. But for this physically informed, we actually use EM solvers, like those methodologies that are shown, FDDT and FEM, as data. Then we train it through the deep ONNet to predict the fields, and the solver computed field across the spatial points and design. So the loss function is the same thing. Actually works the same like any PyTorch on TensorFlow. You have the you have loss function. You use MSE or wherever you can use loss function as suitable. And again, we have the optimizers such as Atom and initial learning rate. That's always you're free to tweak with the batch size. So it's pretty much the same as any deep learning works. Now the computational setup. See, this is a different problem, right? When we trying to compute anything simulation that interact with physics, we come with this issue of computational. You need specific hardware. You can use a CPU, for example, but by using the techniques of like parallel computing, such as MPI or OpenMP, right? With a sample CPU, without knowing those methodologies, it would be hard to train that model. Or we can use a GPU. This is just an example, NVIDIA 100 Tensor. We can use any GPUs that can work better. So the software, we can use a TensorFlow or even PyTorch, and those libraries are available. And for the like EM solvers, we can use MEEP. This is a Python library. Actually, is binded with C++ that help us, and we have this library to import that help us to use those FDDTs, the EM solvers. This console, sorry, that's actually a software 3D simulation. We can use the CUDA and DNN for GPU acceleration as well. That's why it applies for deep learning as well. Here is a case study, right? Waveguide splitter. So just avoid all that. I can show the image. Um, yeah. So this is what is a waveguide, right? So as I shown, all this part to the left is just a simple waveguide. Now we want to split this waveguide, right? But this is a big challenge, right? It's not as straightforward as it seems. We want to know where is even this, you see this edge in here? That's a problem. If this is very sharp, it influences all the waveguide shape and direction, etc., and losses. Just to know how this what we call that in photonics a buggy splitter when it's too sharp, right? This is a very bad practice. Just to know the shape of this bounded boundary, it's a lot of experiment, right? So if we use this deep ONAD, for example, to give us the properties, how far we want to round it, it solves a big problem. This is a big challenge in photonics. It's not that straightforward. We want to split this waveguide. We want to share this lights for different purposes, but just knowing the length or the round area of this one is challenging. So this deep ONAD can help on that. I actually started doing experiment. We're still doing research on that. I tried the genetic algorithms, the gradient based and deep ONAT, and I found out the deep ONAT is much faster, efficient compared to the other models. So just to note, and there's other models like PIN and IPIN. Those most used for physics, but it just found out this deep ONAT is more efficient when it comes to electromagnetics and waveguides. So this is just discussion. As I spoke, deep ONAT was much efficient in terms of timing, especially when it comes to compared to genetic algorithms and gradient descent. Now the computational challenges. So we have a memory bottleneck, right? So solving Maxwell equation over fine spatial grids requires storing large field matrices. We have as well exponential time growth, right? With traditional optimization like genetic algorithms experience exponential increases in computational time. Right. Yeah. So we have always computational challenges. So the best practices and hardware matters in this area. Um, so now what is the future vision is we want to use the electromagnetics large language models like LLMs. We want to use the processing memory, PM computing. We want to use advanced operators learning as well with the experiment and a hybrid physics AI framework. Those are just into research. We're working towards them. Yeah, so I think I spoke already about this one. So I just would like to thank Professor Dr. Shaheen for providing the foundational idea and inspiration behind this work. Their guidance and insight on the challenges and opportunities in large-scale inverse photonics design have been instrumental in shaping this direction of this research. That's pretty much for me. If you guys have any questions.
Do we have any questions for the audience? Or you can put in the chat. We have 2 minutes. Oh yeah, we have a question from Hammond. Yeah, you go ahead. Oh,
Hey, thank you, Shalin, for your sharing the experience. Research on it. So I have the question regarding machine learning models that you have mentioned. You're going to use L1 and L2, and along with you also mentioned gradient descent algorithms. So here, what the problem that you'd like to solve actually?
Okay, sure. So basically, I know this is kind of if you're not in it's a new topic, it's hard to actually absorb all that in 5 minutes or 10 minutes. Yeah. So is the design right? As explained, like in waveguides, right? We have a shapes, right?
Yep.
We have those shapes, and the light travel through those shapes. Okay. So those shapes, when it comes to design, we draw them. When we do simulation, we draw them with softwares, of course. Um, But the biggest challenge is the losses. We in all this area of photonics, we want to minimize the losses of the light, right? We want to optimize more losses, make it much faster. Um, and it's all about drawing of those shapes and how the curve on those shapes as well. We want to know what is the best wave length and width suitable for that waveguide to the light travel in the best way, basically, right? This is we want to get these properties to design that chip or those waveguides, right? We want to know what is the best length, what is the best width, and what is the best curve, because we're going to initialize those when we draw in them to have our light travel through by minimizing the losses. This is what we're trying to solve with this inverse design methodology, basically, overall. If that's responding to your question.
Yep.
Yeah.
Last question. So why don't you go with machine learning and why you are choosing?
Yeah, this is, so as I mentioned before, yeah. So deep learning are not efficient because to solve a physical problem is not like using like pricing and get the data and you train it. It's not that straightforward. To use a any physical problem, not only photonics, you need methodology solvers, as I mentioned, FDDT and FEM, finite element methods, especially when it comes to simulation, right? Like light, waveguides. It's not just data. They are waves. They are they are materials. They interact with the physics laws. So that's what comes this informed physical models to have that deep learning. Then that deep learning will interact with the physical laws to come up with the best outputs. They're not just data as any data. They are physics problems. They're interacting with laws, physical laws. That's what these models are made for solving physics problems.
Oh, sure. Got it. Got it. Got it.
Uh,
Thank you.
All right. If you guys have more questions, you can put in the chat. And thank you, every presenter here. We still have more presentation this afternoon. You can join as well. Hope everyone have a good lunch. And I will stop the recording.